Hello everyone, welcome back to my YouTube channel. Today we are going to go over a conceptual question in mechanics of materials. Uh, Part A says, a simply supported beam with a triangular cross-section is loaded so that it has the bending moment diagram shown below. External loads are not shown in the diagram. The y-axis is defined to be 0 at the neutral axis, and they want us to find at what x and y locations does the maximum tensile flexural stress occur, and at what x and y locations does the maximum compressive flexural stress occur. So first, let's do an overall review of our bending moment diagram since the convention is not as intuitive as we would think. For instance, if we have a simple beam under 3-point bending conditions, so here's a beam, oops, and it's not straight. Here's a beam and it's under 3-point bending conditions, and the two ends are fixed. So load P is applied exactly at the center of the beam, and these two ends are fixed. So our and we'll call this load P, and this length L over 2, and the overall length L. Now we will begin with a free body diagram of this beam under 3-point bending, and it's under 3-point bending because when we apply the force like this, the beam will bend like this. So if a stress element is at this point, it will be under compression since the beam is being squeezed but when a stress element is under the bottom, it will be in tension since the beam is being pulled, it is like flaying outwards. So a free body diagram will look like there'll be a moment at each of these fixed ends since a fixed end applies a moment since the beam is not free to bend in either direction. And we will take the convention of counterclockwise moment as positive, so we will assume that all moments are positive at the beginning. And this point is A, this point is B. So MA is this moment over here. And we'll also have a moment at this end B because the end is fixed. Um, and basically, we have a reaction. We also have a reaction force AY and BY. And we of course have our applied load P. So from our equilibrium equations, we can see that Fy is equal to 0, is equal to AY plus BY minus P is equal to 0. And we here define the x-axis as positive and y-axis as positive, y-axis pointing upwards and x-axis pointing to the right. So from symmetry, we can see that AY equals AB is equal to P over 2, and BY is equal to P over 2. Now we have our sum of moment equation as well, which is going to be, we can take the moment around A. It's going to be MA plus MB, um, and then P is going to produce a negative moment because it will produce a clockwise moment around A, around the pivot point A, at a R length of L over 2. So P times L over 2 is equal to 0. Now we can try to draw our shear force and bending moment diagram. So our shear force diagram is pretty intuitive. It's going to follow the general direction of our shear force at a given location. So our shear force first begins at P over 2, since the reaction force at AY is pointing upwards and at P over 2. So there's going to be a jump in the shear force at this point because shear force points upwards. It's going to start at P over 2, and here we have L over 2. And after that, there is a drop of P. So we will drop to about, mm, we will drop to negative p over 2 over here. And why is it not p? Well, it's because um, we basically start with positive p over 2 and then we experience a drop in p. So it'll be p over 2 minus p is equal to negative p over 2. So that's why we end up here. And this will continue until L, which is when our beam ends. And some people also draw a line going up, returning to 0, which is technically correct if we are considering our if the bounds we are looking at is actually x from 0 to L inclusive, but we can also look to less than L. And this is the graph for x is greater than or equal to 0, less than L. But if it was greater than or equal to L, we would go up because we will be evaluating the shear diagram at that point too. So now for our bending moment diagram, and the bending moment diagram is where things get more confusing. The bending moment diagram is a little counterintuitive. So how we can make it less counterintuitive is to find the moment from looking at our shear force diagram. Remember that moment mx is in general equal to m0 plus the integral from our lower bound to upper bound of our shear force multiplied by dx. So we have two segments over here called this segment 1 and this one segment 2. So m1x will be equal to m10 plus the integral from 0 to L over 2 of the equation for Vx in this segment is simply P over 2 dx. And of course, this integral will be equal to m10, which is basically ma, since we start with a moment here because there is, if we break this free body diagram and just look at the system as the beam, there is going to be a moment applied at each end since each end is fixed. Note that this is not going to be the case if the end is a pin.
What times are exam?
So because a fixed end prevents rotation in this direction or that direction, but a pin does not. So we will get MA plus P over 2 x as our general equation. So we can see from this equation already that our moment diagram is going to have a positive slope. So if we graph our moment diagram, it's going to look something like this. So if we assume MA to be positive, which it is going to be positive intuitively because this beam is bending upwards. So we are going to have, and thus it has a clockwise rotation. So we're going to have a moment counterclockwise at A in order to counteract or like kind of bend this end down, like bend it down basically, which will be counterclockwise and positive. So MA is going to be somewhere over here. We don't know the exact value because this is just a problem without values. MA, and then we're going to have plus P over 2x, so sloping upwards. Oh, wait, sorry. This is where I forgot to tell you about the counterintuitiveness of this problem. So MA is positive and counterclockwise. And because of that reason, is actually going to be on the below the y-axis. Because when graphing the moment diagram, if we have a positive moment here, we actually um in our bending moment diagram for if we have a if we have a positive moment in our free body diagram, we actually drop down. So it will be negative MA over here. And then we have a positive slope because P over 2 times X is a positive slope. And we end up over here. Now we can find for our second segment what it's going to look like. Basically, M2X, which is our second segment over here, is going to be equal to the moment value at this point, which is equal to MA plus P over 2 times L over 2, which is equal to MA plus PL over 4. So our M2X value equation is going to start at the our value is going to start at MA plus PL over 4 and then plus the integral from L over 2 to L of negative P over 2 because we have negative P over 2 here, x dx. So it's basically equal to MA plus PL over 4 minus P over 2, oops, not x, just simply negative P over 2. So negative P over 2x. So we notice that it's a negative slope. So here we have our same value here. And then we just have the same negative slope down. And then we can find our value at L if we want by plugging in L into this equation to get MA plus PL over 4 minus P over 2, PL over 2. So this is equal to MA minus PL over 4. So how to understand this is that basically we end up at the same position. Because MA plus PL over 4 is MA and then we go up by PL over 4. And then here we resubtract the PL over 4. So we go down by PL over 4. I'm sorry, this is supposed to be vertical. Yeah, so if we wanted, we could have added another solution at the L spot, but like I said earlier, we're only considering the bounds from x is greater than or equal to 0 is less than L and not less than or equal to L. So from this bending moment diagram, we can see how the moment in our free body diagram relates to the moment in our moment diagram. So I think this moment here does not appear in our bending moment diagram because we did not choose to consider less than or equal L. So at the equal L spot, we are not showing this moment on this graph because of how we are defining our bounds to be. However, if we look at our free body diagram, we see that a positive moment on our free body diagram corresponds to a negative moment here. So always go by integration because integration never lies. So let's say we had a moment here applied counterclockwise at the location L over 2. Then this would have corresponded, since it's counterclockwise over here, the moment here will be a drop, not a rise, although counterclockwise is positive. So it will have dropped some value if there was a counterclockwise moment here. If the moment at L over 2 was clockwise, we would actually have a rise in the moment. Although clockwise on the free body diagram would have been negative because it was clockwise. Now, this is different when we are considering how the moment is bending because when we apply a force P to this beam, the beam is going to warp upwards like this. So it's actually a clockwise moment here and a counterclockwise moment here. So the clockwise moment indicating it is bending counterclockwise because it's bending up corresponds it has the same sign as our moment here because it's negative counterclockwise, but it's also negative on the moment diagram. So just keep that in mind for evaluating this problem. So enough of our theory previously. We're now going to be going through this problem. And so at what X and Y locations does the maximum tensile flexural stress occur? So remember, if we have a positive moment here, it means that on this bending moment diagram at this point, there is a not counterclockwise, although it's positive on the bending moment diagram, but rather a um, a negative counterclockwise moment. However, the way the beam is bending is as if so the way the beam is bending at this location, since there is a clockwise moment, which corresponds to a positive over here, is the beam is going to be bending like this. Or sorry, not like that, but rather it's going to be bending. Wait. Yeah, so this moment corresponds to a basically a moment of kind of counterclockwise. So I guess the best way to see what this really means is to draw the diagram for the cross section at A and at 2A. So at A, we have our location of the location of the centroid is at this location over here. They nicely gave us the centroid, and then at this point, since um the bending moment here is positive, it corresponds to a clockwise rotation. So in order to get that clockwise rotation, Mm. in that clockwise rotation, this clockwise rotation corresponds to as if if the moment were external, it would be clockwise because uh, a clockwise external moment corresponds to a positive moment on our bending moment diagram because the bending moment diagram and shear force diagram are both graphs of the internal loading. So one way we can understand this, and this is very important that you pay attention here, is that if the external moment is actually clockwise, there must be a counterclockwise internal moment to balance it out. So for this problem, we can simply use read off the values from our bending moment diagram. So if the moment is positive at A, it means clockwise moment at the location A. And a clockwise rotation at a clockwise internal moment at A is going to correspond to the beam bending like this. Since we have a clock a since we have a counterclockwise moment, internal moment at A. So the beam is going to bend like this, and thus uh, the stress state at this bottom location is going to be in tension, while the stress state at this location is going to be in compression. And we can draw the internal bending moment also with this sort of diagram where we cut the beam over here, and we know that the internal moment must be counterclockwise, which is caused by tensile forces pointing in this direction. Because we, oh wait, no, that will produce a clockwise rotation. Actually, if the arrows point this way. Because why does it produce a counterclockwise rotation is because these arrows kind of like push the beam this way. We go from this direction to that direction. So it is counterclockwise. And each of these are axial stresses. And we see that the maximum tensile stress pointing outwards occurs at the very bottom, which on our cross-sectional area is at negative 2h over 3 because they set the origin to be at the centroid. So that's why we have negative 2h over 3 here. And it occurs at A because A is when there is a counterclockwise internal moment, which corresponds to the beam bending upwards like this smiling face. Um, smiling face. And why does a positive internal moment correspond to a smiling face? This is given by our sign conventions for internal loadings, which are different than our sign conventions for external loading. For external loading, we commonly take the positive x-axis to be pointing to the right and the positive y-axis as pointing upwards. But for internal loading, it is different. For internal loading, we have shear force downwards, looking at the beam cut from the left side as positive, and our counterclockwise moment when looking at the cut beam from the left side as positive. But if we are evaluating our beam from this side, the positive shear force direction is positive and our clockwise moment is actually the one that is positive. So these are sign conventions for internal loading. And for internal loading, a moment bending downwards, which corresponds to a clockwise rotation, um, is actually the one that is negative. So the sign conventions for internal loading is different from the sign convention for external loading. Um, and our stress at any given point is given by, remember, sigma x over here is equal to negative my over I. The negative over here, I would not put it because it it tells you whether the stress element is in tension or compression. Over here, I would usually remove the negative sign first and get the sign convention from from logic and intuition of how the beam is bending. As we see over here, since we have an internal clockwise, counterclockwise moment, the beam is going to be in tension at this lower point over here. So the maximum tensile flexural stress is going to occur at x equals a and y equals a height of negative 2h over 3. Because our max moment occurs at a, we see we have a peak there, and the y value is going to be the maximum tensile stress is this arrow over here at a height of negative 2h over at, well, let's just use 2h over 3. And then it's going to be the moment of inertia of this triangular cross section around its centroid, which is constant for the whole beam. So we don't have to worry about that part. We only have to worry about the numerator. And we want to try to maximize the numerator for tensile flexural stress. And for part 2, where does the maximum compressive flexural stress occur? It will occur at over here because over here the internal moment is clockwise while the external moment is counterclockwise. So since the internal moment at x equals 2a is clockwise, this means that the beam is bending like this. And so we want to find this stress element is in compression. So at 2a, we have maximum compression also at a height of 2h over 3. But this time, the stress at this point will be negative. Because it's in compression. But here, the stress state will be positive because it is in tension. So I hope that going through this conceptual question helped you guys. And here's a review of like our theory before going through this problem. And feel free to like this video and subscribe to my YouTube channel for more updates. And see you in the next video.